We now have Ruth Gregory from King's College London, who's going to tell us about black hole thermodynamics beyond a black hole.
Thank you. And thank you also to the organizers for the invitation. Toronto is certainly putting on its best face. The weather's absolutely glorious, and it makes a nice change from what was rather grey and rainy Britain when I left it. So thank you. So today I want to talk a little bit about some work that I've been doing on thermodynamics of accelerating black holes. And in essence, the reason for saying extending black hole thermodynamics beyond the black hole is that this is an example of doing thermodynamics with black holes where it's a composite system. So it's somewhat different. And I guess I've been fascinated by the C metric, which is the metric of an accelerating black hole, for quite some time. And so this was, if you like, a sort of return, blast from the past, returning to some sort of ideas or things that I'd done in the past. So I have some of my partners in crime there and some of the papers, at least that I'll be talking about today. So I thought that might happen once it started recording. Okay, so what I know this is quite a mixed audience and definitely biased towards the mathematical end, but I think one of the things that's always fascinated me about black holes is they're like this perfect marriage of maths and physics. And it's really remarkable that something that is so simple that we can get off the shelf, like a Schwarzschild metric or the Kerr metric, really is describing that object out there at the center of our galaxy, at the center of other galaxies, and also sort of more stellar-sized black holes out and about. It really is, a black hole is a beautifully simple object. It's just amazing that we've actually, usually physics is all about compromise, but black holes, you barely have to compromise at all. And I think black hole thermodynamics is also interesting because it's this really odd mix of the classical and the quantum. If I look at most papers on black hole thermodynamics, the techniques and the approach is very classical in nature. And yet it's sort of really getting to the heart of the problems that we have with quantum gravity. So things that, this idea of unitarity that so many people are so hung up on really does give us problems when we think about black hole thermodynamics. So I think they're just brilliant objects to study. So what's the outline of my talk? I'm just going to start essentially with these preliminary thoughts. I'm going to then just give a brief kind of primer on accelerating black holes. I know many in the audience will be friends with the C metric, but perhaps not everyone. So I'll talk a bit about the geometry. Then I'll get to the work that we did, which is really about doing the thermodynamics of tension. And you'll see what that means when we get to it. Then accelerating chemistry. So we've gone even beyond physics to chemistry here, where this is really just a label about how we describe the thermodynamics, rather than thinking about the geometry and geometrical parameters. We actually try and just stick wholly within the thermodynamics of the system. Then that allowed myself and Andy Scoynes to prove a new reverse isoparometric theorem. So I thought, gosh, we've got a theorem. I really ought to actually bring that out for this talk. And then I'll just quickly at the end say how we can extend it just beyond the simple C metric. So just a couple of preliminary thoughts, which I've already mentioned some of. This idea I said about the techniques being classical. So typically, when we think about proving, say, a first law of thermodynamics, what we're kind of doing is using these properties that are of no-hair theorems. The idea a black hole is very simple, which means our solutions have very few parameters, and we kind of know what our solution space is for the black hole. So if we change our black hole by throwing something into it, what we're doing is we're moving from one solution in that solution space to a nearby one. So that's the idea. And so this is just an example of that process. Let me take a Schwarzschild ADS metric. So this is our geometry. That's 4 dimensions, just for the sake of explicitness. And our Newtonian potential function, our f of r, has the minus 2m on r. I'm just setting g equals 1 for sort of making the expressions cleaner here. And that's our mass, or what we say is the mass. And the plus r squared on L squared tells us we're in ADS, so L's our sort of curvature scale. The black hole horizon is defined by f equals 0. And if we throw something into it, then our horizon will still be defined by f equals 0. And so we simply look at f, where the horizon moves out a bit. We express it in terms of changes of the horizon scale, the mass scale, and the length scale. And then we look at rewriting those. If we want to find the temp, yep, sure. Mm-hmm.
So what is the angular part that this something you wanted?
Okay, so it comes later, but it's the metric on a unit 2 sphere.
So it's just the standard round metric.
Standard round metric. At this point, it's this, because it was the standard round metric, I didn't write it out explicitly.
Sure.
I should have known better.
And just remind me, what is ADS?
So ADS is a space-time with a negative cosmological constant, and so it's got negative curvature. So it's a solution to the Einstein equations
The vacuum Einstein equations.
with a cosmological constant. Right, let me think. Yes, I've got to define everything. Change. Sorry? Yeah, A stands for anti-de Sitter. And I'm sorry, again, I know it shouldn't be a capital A because anti was really with a small a, but this is the conventions from the string theorists. So anything else I've forgotten to define here? ADS, blah, blah, blah. Right, okay. No, it's fair enough. I think it's, so there's a reason I've chosen to use this anti-de Sitter, the negatively curved space. It's because I will be needing to do anti-de Sitter later. And so I'm introducing it now. I'm also wanted to sort of sneakily introduce here the concept of changing L. I will admit that from the perspective of Einstein equations with a cosmological constant, this looks like a daft thing to do. However, if you think of a physical manifestation of a space with a cosmological constant, that is often represented as a vacuum energy of some scalar field. So just like in inflation, we have a positive vacuum energy. I'm sort of imagining that it's possible that the vacuum energy is defined by a scalar field, therefore it can change. And in particular, in ADS-CFT, you do get changes. You get flows from one negative cosmological constant to another. So I know that that's something that always looks a bit strange if you haven't met it before, but it's actually quite easy to implement. Correct. So this is one of the, this is going to be the thermodynamic mass of the black hole. Now, when back in the 70s thermodynamics was being developed, this was believed to be the internal energy of the black hole, mass. But when you have a cosmological constant, it's actually the enthalpy. So at this point, I'm saying that if I change my horizon radius, I change the area, and therefore, since there's this sort of knowledge that area is entropy, that's going to change entropy. This changes this little parameter in the metric, the big M. So this is the geometrical parameter, the parameter in the space of space-time solutions. This is the thermodynamic parameter. L is the curvature length scale. It's a parameter in the metric. Lambda is the vacuum energy. So these are, in the end, this will label the sort of vacuum energy as a pressure, but it is in the sense that it's the lambda g mu nu part of the metric. But in order to change lambda in reality, I would have to have a mechanism for changing it, which requires that it's not really a constant. It's actually something from it's derived from a vacuum energy or something. Right. Okay. And now I'm coming back and going back to some of the things I'd written on the previous slide. So what we learned in the 70s was that if we wanted to make thermodynamics in the universe consistent, we had to assign an enormous entropy to the black hole, proportional to the area. All that enormousness is hidden because I've set h bar and c to 1. But nonetheless, S is the area over 4 in these units. And T, when we want to find the temperature of the black hole, we almost never actually do it by looking at field theory on the geometrical background. We simply Wick rotate to Euclidean time and look for a regular horizon. Gives us a periodicity of Euclidean time, which you actually saw in Robert's talk. And that periodicity of Euclidean time is associated with a temperature. Now, there's all sorts of slightly wobbly steps in that process, but nonetheless, this is how it's done. This is the trade, if you like. The cosmological constant, I'm going to badge that thermodynamically as a pressure. So if we have a vacuum energy, that means we have something times g mu nu in the stress tensor, then our pressure is equal and opposite to the energy in terms of the energy momentum tensor. So rather than talking about lambda, which is in the Einstein equations, I'm going to badge that as P. So that's coming back to the question on the previous slide. And of course, because lambda's negative in anti-de Sitter, that's 3 over 8 pi L squared. So that tells me my thermodynamic gizmo is this P. L is my parameter in the geometry. And then I go back and look at the things that were in that variation of F, and I get that delta little m is T delta S plus V delta P. So that's like a first law, except m is the enthalpy. So even though it's the enthalpy, we kind of still would badge it as a capital M. So here I've tried to emphasize that deriving the first law is really more about looking at the solutions. It's often looking at consistency of variations when you're defining the thermodynamic charges, that M tends to end up being enthalpy. And there's really nothing quantum that I haven't sort of really done anything deeply quantum mechanical here. And yet, what you end up with when you do this is a sort of set of charges that actually do tell us something about quantum nature of space time. Yes.
Would everything be the same?
Yeah, except your, yes, but your pressure then, if lambda was positive, P would be negative. But this all, I mean, I'm doing it, I wanted to do it, you'll see why I wanted to do it in ADS in a bit. But yes, it really is blind to the sign of lambda. And indeed, I did some work with Jenny Trashen and David Castor, which looked at de Sitter with a rolling scalar field. So black holes in essentially slow roll inflation, and you see the thermodynamics actually working out really beautifully there. So, and I guess one of the things that puzzles me also is, this is again thermodynamics. If we, we've started in GR, we've derived these thermodynamic parameters. If we think about S as an entropy and area, that then tells us things about, we can use our thermodynamic intuition to then feed back and tell us things about geometry. So it's all sort of very, almost magical. Okay, I need to move on. Accelerating black holes. So from a physical perspective, it's a bit strange. If you meet an astronomer, they're always, how do you accelerate a black hole? Because how can you push it? Because if you try and do something to kind of lasso it, then anything you throw at it surely will be absorbed. So the only way you can actually have something touching the event horizon is if it's locally traveling at the speed of light. And in order for that to not kind of keep being accreted onto the black hole, your local energy momentum where it touches has to have the energy equal to minus pressure. So the energy has to equal tension. And we have a candidate for such an object, which is a cosmic string. Now, I don't want to get into too much of the details about cosmic strings. I've been asked to talk here next week about these. But a cosmic string is something that is roughly linear. It can result as a vacuum defect in a field theory with an appropriate broken symmetry. And the energy momentum is approximated by a delta function. And I say approximated, that's a slightly iffy thing to do in nonlinear theory, but what it does, if you have this effective energy and tension, you get what more or less a conical defect. So the deficit angle that gets cut out is related to the energy per unit length of the string. So there are no long-range tidal forces, just some global effect. So that's this physical object that produces something that's essentially a conical deficit. Now, this is, again, a metric, the C metric. So this is an accelerating black hole metric in this anti-de Sitter space. You see the anti-de Sitter from this bit. And it's now I've written out that theta and phi part of the metric because it is modified, it's distorted. So we don't have d theta squared plus sine squared theta d phi squared. We have this modification. So there are two parameters in here, a little m and a capital A. So that's one modification. The other thing I just want to draw your attention to is that I put a k in there because I want my phi coordinate to have periodicity 2 pi. So if I'm scanning through solution space, I do not want to have a different periodicity for one of my coordinates as I wander through solution space. So I want to have my sort of TR, theta and phi having the same types of meanings with all of the shifting in the geometry being encapsulated by explicitly by parameters in the metric. So here we have an M, we have an A, we have an L, and we have a K. So those are the parameters. In this case, there's no charge and no angular momentum at this point. So this is a particular, it's not actually the traditional relativist representation of the C metric. It's just a sort of coordinate transformation thereof by Hong and Teo. And the reason being that it's slightly more intuitive, but in the end, it sort of has the parallels to the thermodynamic parameters are direct. So here is my f of r. F tells me where my horizons are, and this conformal factor out front tells me that my boundary, so The Poincaré disk, normally when you look at it, has a sort of nice circular boundary, and that's usually, let's say, taken as r goes to infinity. In this case, my boundary isn't necessarily as r goes to infinity, it's when omega goes to 0. So just hold that thought. It's a conformal factor, yeah. So,
in what sense is this supposed to be accelerated?
So what I'm going to do is deconstruct it and just look at the effect of the parameters. So at the moment, all you can see, if you look at it, is what have I done? I've twiddled with the two-sphere, I've deformed it. And actually, as we'll see in a moment, I've deformed it so that the poles are now potentially have conical singularities. So that's one thing I've done. But that only happens if MA is non-zero. So if M is 0 or if A is 0, it's not deformed. Then the other thing I've done is I've changed my F with this factor here, which could, because if I think about this term, it competes with that term, it could actually introduce a horizon. So it changes what, the behavior. And then, of course, there's a conformal factor in front. So let's start by setting A to 0. Sorry, I said it's deformed. My apologies. It is, this K is still potentially. So if I set A equal to 0, and then I look on the axis through the black hole, I see expanding near the poles where I'm taking, well, I'm really looking at the North Pole here, but same thing if you just take pi minus theta at the south. So I don't quite have an origin of polars because I've got this 1 over k squared. And so what you see is this actually corresponds to a conical deficit delta of 2 pi into 1 minus 1 over k. If k is 1, then delta is 0, and that is fine because then I have the origin in polar coordinates. But as we increase k, we cut out an angle, and if k is less than 1, we have a negative delta, which means a conical excess or a strut. So that's the same thing happens at the north and south poles, and so that's, if we interpret it, it's a string running through the black hole. So the exact metric with the conical deficit was explored by Ariel, Ford, and Vilenkin, but then myself and Anna Chukro and Konrad Kaiken showed how you could replace that with a finite width sort of vortex in the abelian Higgs model. So now let's look at what happens with A. So this A encodes the acceleration, so it comes in G, it comes in omega. So first of all, let me set M equal to 0. So again, I'm not having that distortion to the same extent. What you can do is you can do a coordinate transformation, because remember the boundary is at omega is 0. So what you want to do is have the boundary at some radial coordinate going to infinity, and so that's that capital R. So I can do a coordinate transformation to get global ADS, the only proviso being that what I call T in my original solution is not the global ADS time. So there's a rescaling, and that turns out to be important. So that is that's sort of saying that M equals 0, A non-zero, I've got a coordinate transformation of global ADS, and this is what it looks like. So again, you can think of this as the Poincaré disk, but here's my boundary, the thick black line. The blue lines are constant thetas in my original system. My origin in my original system is not at the center of ADS. So if you maintain yourself, hover away from the center of ADS, you're actually in an accelerating frame, just like we are here on Earth. We're kind of staying at a fixed distance from the center of the Earth. We're in a locally accelerating frame. And so where we stand is related to A. So that's the acceleration. So if we put it all together and we now say, look at adding in an M, what we see is that we have different deficits at the North and South Pole. And so that means we've got an imbalance of tensions. And so physically, if you have an imbalance of forces, you'd imagine something would accelerate. And that's the interpretation of the accelerating black hole. I just want to point out, usually people make one axis regular. In this case, I put the North Pole regular to get a positive deficit angle on the South. But that's a constrained system because you've imposed a constraint. One axis is regular. So this is what it looks like. On the right-hand side, that's a sketch cartoon of our accelerating black hole. It's a black hole displaced from the center of ADS with a conical deficit running from the black hole to infinity if I make one axis regular. That provides the force to keep the black hole stationary, and my boundary is now also distorted. The reason I wanted ADS was precisely to have this static solution here, because the general C metric and the C metric that you use if you're in vacuum no cosmological constant, that has an acceleration horizon. And we didn't want to have any ambiguity in terms of thermodynamics, so we took this slowly accelerating black hole. Okay, so that's the solution. So thermodynamics of tension. So I'm going to go back to, again, not acceleration, my Schwarzschild ADS. I have the same relation as I had before, so what's the big deal? What's the tension doing? Well, if you have a string running through a black hole, you cut out a deficit angle. So you don't have a round horizon, you have a rugby ball, American football type of horizon. And so my entropy actually has this factor of K in it. So if I want to relate the shift in the horizon radius to entropy, I've now got an additional term, delta K. So I have to ask, well, what if K changes? What is changing? That's quite simple. K is related to the tension of the string. And so I see that my delta K can be replaced by delta mu. And then, of course, I've got that, the pressure term. And so I get a first law, which has a TdS, a VdP, but now it's got this extra term times delta mu. I identify my thermodynamic mass, or enthalpy now, is m over k, and I end up with that first law. I have a SMAR relation, and if I look at what multiplies my delta mu, I have what we call the thermodynamic length. So this r plus minus m in this case is a length that is related to the tension of the string, just like the vacuum energy has a thermodynamic volume. So we've now introduced this new potential for the charge mu or delta mu. So this also kind of backs up this notion of m as enthalpy. If the black hole grows, it's swallowing up some string. And so we have to include that in our energy budget, just like it swallows up some vacuum energy. So that's what the thermodynamics of tension is. And at least in this case, it's a very straightforward computation. And just to show, I mean, I said before how you could change lambda if you want to imagine how can you change the conical deficit. One possible process is having a string being captured by a black hole, but then the momentum of this relativistic string pulls it off. And then you find that by requiring essentially, the minimal thing you can do is not to decrease entropy, which turns out to be the same in this case as delta m is 0, because I'm doing this in vacuum. So you kind of look, your delta mu is mu if it's a small deficit, And so as the string pulls off, delta mu is minus mu, and you kind of follow through the first law, you see the black hole increases its mass by essentially the sort of length of string that's been captured inside the horizon. So back to the accelerating black hole. I've kind of gone through it slowly for a sort of simpler metric. I'm not going to go through in detail because it's not particularly illuminating, but I just wanted to show you the general family of accelerating black holes in these Hong-Tio coordinates. So Plebanski-Demiansky kind of went over this, and I guess in the past it was just Weyl type solutions. Yep, go on.
So this accelerating black hole, it's sort of tethered to something far away by this string, is that right?
Yes, that's kind of the picture to have.
And that's what's accelerating it.
Yeah, the string, and it's accelerating but not moving because of the negative curvature of ADS. So this is the general metric. You can see that there's now a little a, so that's rotation. A little e, I could put in magnetic charge, but it doesn't add any value. That means it's charged. L, ADS, negative cosmological constant. Capital A, acceleration. And little m, the mass of the black hole. So this is the all singing, all dancing, rotating, charged, accelerating metric. Black hole. Okay. And so I just wanted to draw your attention to that alpha there. That's reflecting the fact that this time, if we're again going to do it in slow acceleration, but this time will not be the same as the clock of the asymptotic ADS observer, which was very important. So effectively what you do is you go and you vary, you allow all of the parameters in the metric to vary. You know that the entropy will still be the area of the event horizon. The presence of that alpha will change the temperature. So this is ignoring again the charge and angular momentum. If you rescale time by alpha, you've rescaled the temperature. It's also going to change what you mean by the mass. And effectively, when people do black hole thermodynamics, they usually do it via consistency. And in this case, it's quite an interesting algebraic problem, rather lengthy. But really, in order to understand what what alpha is, we had to sort of think, what is our mass? Now, we used a few different ways of thinking about this. For example, we also did an Ashtekar-Das definition of mass. But here I'm just going to briefly say this is more from a holographic or string theory type of perspective. So that conformal factor changes where the boundary is. And so if what we do is we do a Pfefferman-Graham expansion in from the boundary, and we redefine our r and theta as a sort of holographic z coordinate. This is z equals 0 is the boundary and marches in, and psi is like a cos theta, but again, not quite. And so the idea here is that you do an order by order expansion to do a coordinate transformation, but what you want is you want to have your metric near the boundary in a canonical form. So this is kind of the way string theorists do it. So you start off by saying z is your coordinate that defines the boundary. There are no 1 over z terms in the metric, there are no cross terms, and everything that happens in this sort of, in this case, 3-dimensional space. So you can see we're doing a power series expansion in z as we go to the boundary, and then we just pull off the formula that tells us how the energy momentum on the boundary is related to these different coefficients. So it's just a calculation For the boundary metric, we get this deformed sort of sphere, and we can calculate the boundary stress tensor. And we sort of see that it has a sort of radiation type term and then an anisotropic term, which is coming from the deformation. And those coefficients look something like this. And so to get the mass, we simply integrate up. And we see our mass is m on k as before, but it has this alpha term. And so if we look, what is alpha? If we set m to 0 and we look for a round 2 sphere on the boundary, we get this same alpha that we had from the slowly accelerating Rindler formula. Anyway, I think the message I want to get is that we can do this computation, which gives us, if you like, a point on a ruler to tell us what alpha is. And so then it's basically cranking the handle. So this is what we got. In terms of the parameters of the geometry, that is what our thermodynamic mass is. So now that's the difference between capital M and little m. You see it starts off with a little m, but then you get a whole load of extra stuff. It starts off with a m on k, 1 and k term. But when you add rotation and charge, you get all these extra pieces coming in. So it's it's slightly, well, I find that slightly intimidating anyway. But it's, yeah, so I think even I can't remember, did I finally give up on pen and paper for this one? I'm not sure, probably, yeah. So those are the general thermodynamic parameters. However, they're all expressed in terms of parameters of the metric. And so you could sort of, obviously you expect the gauge invariant, but it's not kind of explicit. So how would you, is there a better way of writing these? And so this is the accelerating chemistry part. So I can see time is beginning to tick down. So let me just I refer you to either come back and look at the slides or, or the paper or whatever, depending on your level of interest. Okay, so if we want to kind of think about just doing thermodynamics, forgetting about the geometry that kind of gave rise to this thermodynamic system, what we'd like to do is to express, we have our charges, we have our potentials, and we'd kind of like to express our potentials in terms of the charges. And so an example of this is the Christodoulou-Ruffini mass formula, where the mass, so here it's for Kerr-Newman ADS, the mass is expressed as a function of the entropy, the charge, the rotation, and the pressure. So there's no sort of parameters from the solution or the metric there. And so this was what I did with my student Andy Scoynes, and what we found when we were doing this was that it was more natural, rather than having a north-south tension. I come from the north in Britain, so I don't like north-south divide. So instead, this is a leveling up by looking at an average of the deficits and the differential. Because it is the differential that tells you it's accelerating, but there's also physics associated with an average deficit. And so we then just essentially did a little bit of guesswork and then a little bit of checking about how that Christodoulou-Ruffini formula would generalize. And we found the following chemical expressions. So these are, it's not intimidating, but it's slightly less intimidating. And again, everything on the right-hand side is the charges. Okay, are the charges, is the charges? So that was the result that we got. Now, we kind of did this because we were interested in looking at doing some other fun and games with black holes. I'm going to just skip over those. You can look at the Hawking-Page transition. It doesn't change the temperature, but it changes the free energy. There was a phenomenon of snapping swallowtails that had been observed, but because we had the chemical expressions, we could actually do it precisely and find precise expressions for when the swallowtail snapped. So there was, that was kind of nice. And then I think the nicest thing was that we could prove a reverse isoparometric theorem. So we have the isoparometric inequality in maths, which is essentially saying if you have a piece of rope, the maximum area it can enclose is when it's circular. So that's the sort of idea. Now, this is a problem for black holes, because it would kind of say that a round black hole would minimize the area for a given thermodynamic volume. So that would suggest a black hole was unstable, right? Because area is entropy. So Svetic and collaborators conjectured that in fact in black holes, we don't have an isoparometric inequality, we have a reverse of it. That in fact the trouble is, a round black hole maximizes the area for a given volume. And they demonstrated it was valid for a set of examples. So here, I'm going to just set the charge. I just want to sort of show you, I'm going to prove that theorem by, but in again, a pared down example by setting my charge to 0. So to make it cleaner, X is 8 ps on 3 delta, Y tells you about the angular momentum, and then lifting the expressions for the Christodoulou-Ruffini type expression for the mass and the thermodynamic volume, this is what they look like. So again, it's relatively clean. C is the acceleration. So if I combine this together, I sort of look at this 3mv, I take the C onto the other side, I square it, and I see I've got some of the terms up in the expression for the mass. So I can rewrite my expression for my mass in terms of the volume term and some extra junk. But this is now just completely straightforward to sort of say, well, obviously, because those terms at the end, you're subtracting something, this here, the 4 pi m squared over delta S is less than that bracket squared, but then I know that this term is bigger than that term from the expression for V, so I just say, well, this is just less than cutting that out, so it's less than that squared. I rewrite it just by reordering the terms, and then I can extract from that the reverse isoparometric. So if the delta wasn't there, that would be the reverse isoparometric inequality. You add a deficit and you change that reverse isoparometric. It sort of makes it even more strong. Yep.
Is there any relation to the camera inequality here?
Short answer, I'm not sure. So I have to come back to you afterwards. Can we talk afterwards? Sorry. And just to finish off, because I know I'm out of time, there are solutions of many black holes, many accelerating black holes. Faye wrote a really nice paper on this that I guess I always refer to when I want to look at the solutions. This is with no cosmological constant. And so we take a Weyl form of the metric, and essentially the Newtonian potential is just given by looking at potentials for rods lying along an axis. If you want acceleration, it's a semi-infinite rod. And so what we did was we looked, it's quite a complicated metric. You've got a sum of all sorts of logs of various parameters, which have an expression in terms of these lengths. And so we just looked at that system and varied absolutely everything that we could. And we discovered that there was a composite first law of dm being TdS minus lambda d mu for each segment of string and each black hole. And so, that's our thermodynamic length is just given by the worldsheet volume of the strings between the black holes. So that's really just, I think, pretty much all I wanted to say. This is just an example, coming back to the picture on the first page. that was an example of 3 black holes where the 2 outer ones have the same mass. And you can just look at how the entropies change with the separation. And you see that the thermodynamic length of the strings it's positive at one side and negative in between the black holes. And that's really just reflecting that these things don't act independently. If you change one black hole, you're changing the whole solution. So just to try and come in on time, what I've shown you here is how to have composite systems. This black hole is not isolated. It has a string coming out of it. And so I can do thermodynamics with those systems, and I can also include changing things, properties of the string. So we found a new conjugate variable, the thermodynamic length, and we can, find thermodynamics of accelerating black holes. The technical point to make it work was this renormalization of the time-like killing vector, which actually was introduced by Gibbons, Perry, and Pope first. So then we derived expressions for the variables, the reverse isoparometric. So I'll finish, thanks.